and Karen Dawson will start us off. Karen, the floor is all yours.
Okay. I hope you can hear me.
Yes, ma'am, we can.
Excellent. Well, good morning or good afternoon to some of you. And I'm going to present today about how testing allowed the use of an alternative deep foundation system for urban redevelopment. And spoiler alert, we cut the foundation costs in half and halved the construction time. I prepared this presentation with the help of Vijay Velachemi and Sarah Schultzer. Vijay and I were going to tag team on this presentation, and unfortunately, he had to make an emergency trip to India to care for his sick parents. I'm sure I speak for all of us by saying we're very sorry for this tragedy and wish he and his parents the best. Today's presentation, I want to just quickly go over the project background, the subsurface conditions, the original foundation designed by Langen, who were the geotechnical engineer of record, then describe the alternative foundation system, the pressure-graded helical pile proposed by EMC, the foundation contractor, Pileworks, the supplier, and Jacobs in support of Pileworks for design. Then go over load testing and the results, provide a little bit of case history information about the production installation, and finally conclude with lessons learned. So the project location is in New York City. There's the island of Manhattan, the Hudson River, Brooklyn, and our site is there on the shore of Coney Island. The area has been previously developed. It's a lot of brick masonry construction. The red building is a nearby site that's a two-story brick building. Project background, it's going to be it's about a 15,000 square foot site, 7-story development. There's no below grade levels, no dewatering. They didn't want to change the loading. Columns load ranged between 170 and 800 kips, a little bit more than 200 piles. You'll see there's some very challenging subsurface conditions, and importantly, it's under the purview of the New York City Building Code, which has some fairly significant restrictions on what you can and can't do in reporting. So again, subsurface conditions, these are beach deposits in a marine environment, so it's interlayered sands and then very fine silts and clays. A subsurface profile developed by Langen. There's this surface fill, as this is reclaimed land that used to be underwater. So about 10 feet of fill, and there's a fair amount of debris in this and a little bit of contamination. So minimizing spoils was important. Then we have way to hammer or very soft clays, some silty sands that start out fairly loose and become medium to very dense. More weight of hammer clay or soft clay, more sand, more very soft clay, and finally our bearing layer, which extends at least a couple hundred feet. And this is just a medium dense silty sand. So, you know, the design challenges were they had liquefaction down to about 20 feet. So shallow foundations were out because of bearing loss during the seismic event and also excessive long-term settlement. They thought about ground improvement, but it would have been prohibitively expensive in the, you know, interlayered deep soft clays down to 100 feet. So the solution was deep foundations. There were 2 New York City Building Code compliant foundation options that they considered, a driven pile system or taper tube piles and drilled micropiles. And they selected the micropile option because of the, you know, low vibrations and noise, and because this was a residential and business neighborhood with all this masonry construction. The micropiles avoided the deep driven pile constructability issues. You know, this is a 110 by 180 foot site. So, setting up a crane with high leads would have been a challenge, and there would have been splicing. Relatively speaking, the drag load on a permanent micropile casing through the upper 100 feet would have been less than a driven pile. So that was one of their criteria as well. So Langen's original design was a 13 3/8 inch OD temporary casing, I'm sorry, permanent casing to 100 feet below grade. And then they had a 40-foot long bond zone below that. And it would have been a 200 kip allowable compression load. The contractor came in and they thought that this was a very expensive, very risky foundation. And so they proposed an alternative, a pressure grouted helical pile. And in case you haven't seen these before, a quick show, they shoot grout through the inside of the pile, through those holes in the tip, as they screw the pile into the ground. And the grout displaces the soil and also mixes a little bit with the soil with the helix, and so you have this composite grout steel pile in the ground. As they add additional sections, they stop grouting and add additional 20-foot section of pile and continue the process till they get to the toe. So how do you design a pressure grouted helical pile? Ungrouted helical pile, you have a skin friction on the shaft and you have a toe bearing, and these are calculated in ways that are very similar to a driven pile. For the grouted pile, we like to look at two different methods. The first we call the screw pile method, and it's just exactly like the ungrouted pile, except for we take the equivalent grouted diameter as the diameter of the shaft for skin friction. And typically what they target on these is that the grouted diameter would be equivalent to the helix diameter, but it can be different. And again, the toe bearing is the same as either the helical plate, usually not bigger than the grouted diameter. And another way that we look at it is as what we call the micropile method. And this sounds a little bit backwards, but it's basically that we take a type B micropile bond strength and apply it over the diameter of the shaft. In toe bearing is still calculated the same way. And we kind of present this as a couched design so that, people know that this is variable and it really depends on load testing for verification, and so that we can look at a range of conditions. And it has worked out fairly well with the limited database we have. When they install these piles, as an example of the feedback that you get, with depth, you have the torque that the machine is exerting. You have the grout pressure, the next column over. You have the grout volume, which you can convert to an equivalent diameter. And I've superimposed this, the boring log SPT in values from the nearest boring on the right-hand side. So you can kind of see how this works as you go through these different layers. And we were targeting a grout volume that was a little bit bigger than the shaft diameter through these upper layers where we wanted to minimize drag. They were a little bit unsuccessful on this particular example in that, you get to this very soft material and the grout diameter increased instead of decreasing, but they were able to refine this as they went along. So the details of the alternative pile system were the final product was a 7 5/8 inch diameter steel shaft. It was a 1/2 inch wall. It was a little bit oversized just because of the challenges they thought that it would be to get through some of these dense sands that were in the upper 100 feet. This is recertified oil field steel, so it's 110 KSI yield strength. We had a single 18-inch diameter helix near the toe, a single grout hole just above the helix, and we estimated that the length would need to be between 105 to 125 feet long for the two loading conditions. The layout was the same as the micropiles, but because this had an equivalent 18-inch diameter because of the grouting, we had to increase the spacing on some of the really crowded pile caps. And the contractor estimated that this system was going to save about a third of the protection pile of a third of the time required to install micropiles, and probably 2/3 of the micropile material cost, and it had that additional benefit of really no spoils. So the New York City Building Code is kind of significant here. They have two pre-approved types of piles, and if you are not two, they have pre-approved piles, and if you are within these pre-approved pile types and load conditions, it's a fairly simple top-down load test that you have to do. If you don't meet those requirements, you need to file this special CCD1 application, and there's a review process, and it's a little bit time-consuming and risky. Even with this risk, they still thought that this was going to save them money, and so they went ahead with this process. Now, the load cases we examined to determine how do we test these piles, there were 4 of them, and being geotechnical engineers, we believed in that believe in the neutral plane method. This 4th one would have had a load of about 520 kips, which would consist of the dead load from the structure and a drag load, and there's no factor, and we just look at that for deformation and the structural capacity of the pile. Langen thought that the New York City Building Code people would be confused by this, and so we can, for them, sorry about this slide, this shifted a bit, but case 1 and case 4 were considered the controlling case for this, where case 1 is just the standard non-seismic compression, so you have a dead load and a live load, and you apply a factor of safety, and that's a 480 kip load. And I talked them into not putting a factor of safety on the drag load, but for case 4, then the load went up to 760 kips, and that was only considered for the piles around the perimeter that were next to an existing building where perhaps load could be applied in the future due to dewatering or additional fill. So we went ahead with the load testing. They installed 3 instrumented piles with sister bar strain gauges, and they tested 2 of them according to this very strict New York City Building Code procedure, which uses like the 1994 ASTM standard with a kind of a long loading intervals and a 24-hour hold time, and then after you take the load off, you hold it for a long time. They overloaded one of those piles. There were also some lateral tests which were to a really small load, and I won't go into that here, and tension was planned as a contingency, but because the factor of safety based on our interpretation of the compression load tests was so high, we didn't need to do that. So here's the results of one of the load tests on the first pile that they installed. The blue is the original New York City compliant load test up to the specified capacity with this forever hold time, and then backing off. Then they reloaded the pile up to a little over 1,000 kips, where the toe started to move uncontrollably, and unloaded it. They also, the second pile was a little bit deeper, that they tested up to 760 kips, and again it had similar curve shape to the first blue curve. Didn't fail the pile even close, with load returning to near original value. So I can't talk about load testing without going into strain gauge interpretation, and I'm gonna kind of skip through this quickly, but you'll see that the test on the right, this is for the deeper pile, so we had higher unit skin frictions than we did in the lower layers. It was a little bit problematic because the strain gauge placement didn't line up perfectly with the layer boundaries, but we generally see that the layers that are sandy had increasing unit skin friction, with increasing load, and that the soft clays, you know, had a peak and tapered off as they were, the full skin friction was fully mobilized. So we did the neutral plane construction and found that yes, indeed, we were able to get the loads that we wanted, and we checked settlement was not an issue because the neutral plane is down in the sand. We developed, just for fun, this is a comparison of what we estimated before testing with the actual values that we got from testing. The solid lines are the predicted total capacity of the pile by both the black is the micropile method and the yellow is the screw pile method, and that's compared to this solid diamond for total capacity. The dotted and the hollow diamond are the shaft resistance. So we're pretty close. And again, it's nice to use the two methods to couch, to bracket the load. And again, this blue line is what the New York City building code would have had for our required capacity. So just to summarize what that testing involved, the 3 test piles that they installed took a couple days to install. They waited a week for the grout to set. Every time you set up and tear down a compression frame takes about a day and a half, but you can do that concurrent with some of the test pile installation. The New York City compliant building code test takes about 3 days per test, and that's, you know, with a person there full time. If you do the current standard of practice quick method, it's about a half a day for a test. So I'm sorry if I'm ragging on the New York City building code, but this is something that other jurisdictions do as well. And it would be nice if folks were aware of the impact of some of these decisions. But you know, the New York City building code test, we were not able to test the piles to failure, so you really don't find anything special about your pile. You can't use it to leverage your design. And if you spent the same amount of time doing a quick test compared to this old standard, you could do 2.5 times more testing. We didn't end up doing the uplift tests. And again, just for folks' information, that when you do a lateral test, it takes about a half a day to set up and tear it down, and about a half a day to perform the test. So production, they used 150 kip foot drive head attached to this CAT 249 excavator. They had an on-site grout pump and silo. The grout had a set retarder in it. They had a couple ancillary machines to move pipe around. The piles were in 20-foot sections with API threaded couplings. They put these pretty aggressive teeth on the piles because they were concerned about getting through that dense sand that was in the 30 to 40 foot zone. And at the beginning, the production was about 3 to 4 piles per day, or 330 to 440 linear feet. And it was actually limited by the grout delivery. It was hard to get it through town to their plant. As they went along, normally you would want to install your piles either from the center of a structure outward or from an edge. And they were, because of constraints on the site, they had to jump around. So there were challenges as they got more and more piles in the ground. It was harder and harder to get them in the ground. They densified the soil. So as production continued, they brought in an additional machine with a 16-inch continuous flight auger to pre-drill all of the pile locations down to 40 feet. Everything else was unchanged. They got improved quality on their cement, and they were able to get 5 or 6 piles per day. So the estimated savings from this alternative design, the materials compared to, again, this is the original micropile design, so not a driven pile. But 1.6 million compared to 1.1 million. The construction labor and equipment was 2.2 million compared to 0.6 million. The engineering and testing and special inspection report was a wash for both of them. And you might say, oh, well, with all that testing and especially the owner originally said this, all this testing and engineering support, it's so much more expensive. But you have a special inspector for 10 months instead of 3.5 months. You kind of burn up some of that extra expense that you think. So the cost alone was almost double for the micropile design, and then the permitting took about twice as long with this alternative method. The testing was twice as long, but as you can see, the production installation was much shorter. So they shaved about half the time off production. So what did we learn from all this? I guess a suggestion that I have on all of these is that we build some practice installation into our testing if possible. When you first come to a job site, you have operator, the site is new to them, the equipment is new to them, and now you're installing this precision test piles, and stuff always goes wrong. You can't get the strain gauges in where you want them. It's hard. They're just not as good at it. So it would be really nice if you could find some low capacity piles that don't matter somewhere on the site and use them to do your first 10 or whatever, so that the operators are really good and you have your system dialed in before you install those test piles. Second, plan for more tests than are needed, so that if you, and I know instrumentation is expensive, but what's $5,000 worth of instruments on an extra pile if it helps you to do the tests that you need to save money? Third, test to failure. There's a big incentive for people out in the field. They have in their mind that they need to go to this certain number. They're in a hurry. They perceive that it's taking forever, and they always want to stop when they get to that magic number. But test until you move the pile so that you can see that you've fully developed your skin friction and your end bearing, so that you can use the results to apply it to something, so that you can change your design a little bit. Fourth, educate your regulatory officials. More tests to failure is a lot better than fewer tests with long holds. Recognize the neutral plane method, so we're all speaking from the same sheet of music. And then, of course, the final lesson is that the testing really does save time and money, even though it might seem like an expensive and an unnecessary expense up front. So that concludes my presentation, and I'd really like to thank the additional contributors, Tassos Papathanassou from Langen, Thomas Rankin from EMC, and Matt Fenwick, Francisco Johnson, and Jesse DeBoard from Pileworks. That's it.
Thanks, Karen. We have a few more minutes, and I thought that you still had 2 more slides if you had some time left over. I don't know whether
I did. I think I had Jamie hide them, but if she can unhide them, I can. If there's no questions, I might.
Well, I have some questions, but we can move those to the Q&A. But if Jamie can unhide those still, then you have a few minutes to talk about those 2 additional slides.
Okay. Are they? I don't think I have control anymore.
She probably took it. There she goes.
So one of the challenges that was oh, can you go back one? Oh, there we go. it's just slow. One of the challenges with this grouted pile is, the diameter changes, and when you're trying to use these sensitive strain gauges, the area is important. As Van Kamerka described at the last super pile, the incremental rigidity method can help you to get around this problem, but you have to test the piles. You have to fully mobilize the strain, and so it doesn't work so well when you have a pile that you don't test to failure. The other problem is this was a cycled loading, and Bengt Flenius and Ruben have talked about how actually there was an article in the most recent DFI journal, I think, about how when you cycle the loading, you just make the interpretation much more difficult, and that happened with this. The incremental rigidity method produced unreasonable results, but we looked at how to pick what the diameter was for this, and it really makes a difference on what you pick. Can you go one more slide?
Sure.
So this one shows on the left-hand side, I said, let's just pretend that this is a shaft of constant diameter that's equal to the steel shaft, 7.625. And what you'll see from these depth versus pile head load is, you get this where you're actually getting load increasing with depth, which is unreasonable. The other unreasonable thing you get is when you convert these to unit skin friction, you get some really high values for skin friction in the weight of hammer clay, and you get some pretty low skin frictions for the sand that was dense. So it isn't a reasonable interpretation. This plot on the right is where we picked the diameter based on, the average through the increment since the last gauge, the gauge above it. And this is a little bit more reasonable looking curve, and the plots make sense. There's some of the ones that are the OHs are showing pretty high values, but it's partially because there wasn't perfect alignment between the gauges, the gauge locations, and the layers. And also we got this, humongous volume of grout into these soft layers, so perhaps that was doing something. But this is one of the challenges with strain gauge interpretation for this type of test. And I think if we could have tested all of these in constant increments to failure and analyzed with the incremental rigidity method, we might have had a lot better, easier interpretation, I should say. That was it.
Okay, thank you. And we'll leave the questions for the Q&A at the end. But thanks for this interesting presentation. And also, I think this is the first presentation that we got in this series about helical piles. So it's nice to have a case study that illustrates that application for that pile type as well.